Hey, hello there. So let's look at today's Leetcoding challenge question. It's called count square submatrices with all ones. So the question is as follows. We have a matrix with ones and zeros. It's a binary matrix, m rows and n columns. And we want to count how many square submatrices that consists only of number 1. So as an example, we have a 3-row, 4-column matrix. And the detailed breakdown about those all one submatrices are as follows. We have 10 submatrices of size 1, so that's basically the individual cells that contains a 1 in there. So it's 9 and plus another 1, so it's 10 individual cell with value 1. That can be considered as the smallest submatrix, square submatrices. And we have 4 submatrices, square submatrices of side 2. That's from row 1, column 2, that's the top left, and row 2, column 3 as the bottom right. That's basically 2 row, 2 column. And we shift towards right by 1 column, we get another such side length 2 square submatrix. We move down by 1 row, we have another one. Move towards left, we got the final 4 square matrices of size side length 2. And finally we got a 3 row and 3 column submatrices, square submatrices. So the total is 10 plus 4 plus 1 equal to 15. And yeah, this question, once you read through and work through the example, if you have done the last month's Leetcoding challenge question, you feel it's pretty much the same as this maximum square. There is only tiny little change you need to do to make it work. But nonetheless, I'm just going to assume that we haven't solved that and do a little bit explanation about how to actually count this. So to reduce simplicity, reduce the complexity, let's just think about the case with no zero and perfectly square. So the way that we count the submatrices, if we just imagine that if we are like a human, we work through this problem from top left towards bottom right. So in the first row, we just count 3. That's basically 1 plus 1 plus 1, the cell value added together. For the second row, if it's when we are in the first column, there is no matrix that we can form, that submatrix we can form that's larger than 1, so that's just a 1 there. Then when we look at row 1 and column 1, the middle element, that element by itself is a submatrix of size 1. And then we begin to see, ending at this location, the middle elements here, we can actually form a 2 row, 2 column square matrix. So we basically should add another one. We can do so, indicate this in this matrix by changing the value 1 towards 2, change that into 2, so that when we might do one last pass to just sum all those numbers out together. To get to the number of matrices. So just temporarily we just change the value from 1 to 2, because this pretty much just means how many square submatrices have a bottom right position in this location. When we move towards right by 1 column, we find a similar story. That cell by itself is a submatrix of size 1, but with that we can actually form another side 2 submatrices. So it's 1 plus 2 plus 2. In the second row, so that brings up the total to be 3 plus 5 equal to 8. Then when we look at the last row, we have a single one, because this is the first column, there's no way you can form anything that's larger than 1, so it's 1. Here it's the same as the those other 2s up there, so it's a 2. And lastly, the bottom right one, we can actually change this to 3, because you can form a single size 1 submatrices all by itself. You can form 2 row, 2 column submatrices, and you can also extend to the whole thing, which is a 3 row, 3 column submatrices, square submatrices. So the last row will have 6, so it's 3 plus 5 plus 6 equal to the 14. yeah, so in this particular case it's a 14, and now our example is just to have an isolated one there, which can only form a submatrices by itself. So the total, now our example total is 15 subtracted by 1, so 14 here. So just by working through this example, if we define that some kind of function, I guess, not really DP. Let's say the row number, column number. Let's say this is the number of square submatrices which has a bottom right location at this row and column number. Then if we can populate this, the answer for this question is basically just we just want to return sum of this function call for row in number of rows and for column in number of columns. So it's basically populating this table and summing all the elements up. And that's pretty much the intuition behind this. There's only a little bit to talk about how we actually look into these numbers. This is a special case where we can just add thing. The number always goes up when we're looking at from top left towards bottom right. What we need to do is to come up with a recursive relationship between FRC and its adjacent values that has been already calculated. So the base case is of course the base case is always that if it's the first row or first column, the FRC is just going to be the matrix value. So that's the base case. Beyond that, then we should think about how do we actually try to form something that's bigger. Let's say that we have something looking like this, 1 1 1 1 with some zeros there, so it's preventing this submatrix to become even larger. So that's 1 1 1 2, and just put some question mark there. We don't know those numbers yet. Then we are currently looking at this X location. At this location, if it's a 1, of course we would want to try to make this number as large as possible, like the 3 here. The way that we can determine how high can we go is to look at the R minus 1 and column minus 1. So let's say this is a row and column, because the best that we can do is just to pad 1 row in the bottom and 1 column towards the right to that size 2 square submatrices. The best we can do at this location, row and column number, is just to pad 1 row and 1 column to make the square matrix to be one size larger. So that would be this plus 1. And it's not necessarily that we can do so, because we need the elements. If we want to be at least the number of rows plus 1 compared to this size 2, we want this two question mark towards the left to be 1, to be actually the ones in this original matrix. We can know so by just looking at the immediate left value. If it's a 2, that means we can actually at least be able to have 2 rows, two columns towards left being ones in this original matrix, so that we can actually pad 1 row towards this compared to this row minus 1, column minus 1 square matrices. So we are kind of restricted by how many ones we have towards the left, and we can determine that number by looking at the cell to our left. And it's the similar story to the to determine if we can actually pad one extra column towards right. That's basically looking at the cell value that's directly above us. So basically, this formula is just taking the minimum between among these three cells and plus one, to get the maximum side length for the square matrices ending at this row column number location. Yeah. So this is the recursive relationship. So that's pretty much it. With the base case and the recursive relationship, it's we can do the bottom-up approach, which is most efficient. And notice that the recursive relationship, the cell values there, the values, the past, the calculated value that we are relying on, it's either the previous column or previous row. So to optimize the space, we can basically only store 2 rows of data. Function called FRC with the most recent 2 rows. Anything that's beyond that, we can discard that. So a little bit optimization on space would be not to actually populating this 2D grid, but rather just only keep the most recent 2. And again, to find the answer to this question, for every row that we populated, we need to sum all the elements and accumulate that. And in the end, we just return that accumulative sum. So that's pretty much the same as the this question, maximum square. That question, it's just looking at the single maximum length. But for this question, we have to accumulate the row sums. That's the only difference. Everything else is pretty much the same. So let's just gonna start this coding this question up. I want to move it up a little bit because my camera is blocking me. So I'm just gonna grab 2 rows. One is the previous row, one is the current row that we're working on. The current one, since that we are going to populate, I'm just gonna make a copy of this, and I think there are we need to initialize a accumulator total, which initially is not 0. We can actually do just directly use the first row because that's not our base case. As indicated here, if the row is 0 to if it's the first row, there's no bigger matrix that can end at that location. The best they can do is just by itself to form a size 1 submatrix, a square submatrix. So the matrix row 1 is basically the FRC with row equal to 0. So we can just directly put that onto the previous and sum those up for our initial total. Accumulate, is that how it's spelled? Yeah. Oh, sorry, 0. And then we're just gonna loop through this matrix row by row. Let me grab the number of rows and number of columns first. Do I need? No, I don't. Row equal to 1, while it's smaller than the total number of rows. Increment this row number, and then we're looking at the column by column. Try to populate this in the same way that we do in our demonstration hand calculated practice here. just gonna use this. So what we do is, if this is the base case where the c equal to 0, you know what? The case is that if the cell value is 0, this current current FRC value at the that column should be 0. So that's matrix row and column. If it's 0, then we're gonna set this to 0. Make sure it is 0. Otherwise, if it's the first column, and since we are in the else, it means that the matrix row and column value that we are looking at, the cell value is 1. I'm just going to be a little bit more explicit here to test the equality. Then we just going to set this to 1 because this is the first row, first column, so it's the one of the base case here. Otherwise, we just do this recursive relationship. Yeah, so anything that's a row above us, we look at the previous. I'm gonna put this into this. If it's the same row, we're just looking at the previous, the column towards left. And the previous row, yeah, we just look up at the previous row's value. So by taking the minimum and +1, we basically trying our best to expand the square matrix to our bottom left. We try to expand that with the number of available columns and the number of available rows that's directly to our left and directly above us, which is indicated by the cells values to our left and above us. So that's pretty much the recursive relationship. Then what we're gonna do is just add this up. We will set the previous, the current row to be the new previous, and gonna add that row sum to the new total. So yeah, so that's pretty much it. Return the total in the end, and that's the code. Let's try run through example. It's working. Okay. Yeah. Yeah. It's a kind of a strange that they have done this quite often now. Today's question, it's pretty much the same as the question from last month, and a few days ago they find all anagrams question and the permutation in string. They are really similar. So a lot of redundancy in the questions selections. Yeah, so that's pretty much the question for today. It's the runtime for this is n plus n, the number of rows plus number of columns, multiplied by the number of columns, because we looking at the individual cells one at a time to explore all the matrix, every cell exactly once. And for the space, we have 2 rows here: the previous row, the current row. And there could be a little bit of optimization, depends on the whether it has more rows or you have more columns to save a little bit of space, but the time complexity is not bring down if we choose to scan this by row or by column. The time is the same. We have to look at the individual cell at least once. The space is the straightforward implementation here is twice the row size. And yeah, that's pretty much it. Yeah. All right.